Welcome to the LED webinar for April, and I'm pleased to present today Ernest Miller and Ron Selvig. I hope I said his name right. We'll be presenting a topic called Using IoT to Drive Quality Improvement in Manufacturing. So just a couple logistics. Reminder that again, there will be another webinar in May 12th, and that will be that's titled My Value Stream and a Journey of Professional Transformation by Joe, I hope I say his name right, Vaca. And that registration link can be found also in the handouts of the GWT control panel. So reminders that yes, you will get continuing or RU credits for this. They will automatically be sent to you via email in about 24 hours after this webinar. So no need to ask questions in regards to that. Just know that those will be sent to you automatically. If you have questions, you will see at the panel on the right-hand side, there is an area to pose questions. You are in listen-only mode, but I will be paying attention to those questions and posing those at the end or sometimes in the middle if the opportunity presents itself and it makes sense. Ernest has 30 years of experience in designing and managing large-scale operations and transformations. He's provided leadership in many areas, including operations strategy and quality improvement. And he's worked for some global companies like Ford, Mitsubishi, NCR, and was also a consultant at McKinsey and then a partner at EY Consulting, leading the operations excellence practice. I am going to let him introduce his co-speaker and co-facilitator and when he starts the presentation. So with that, I am going to turn the presentation over to Ernest and Ron. Thank you so much.
Okay, thank you, Ellen. I think we'll get the slides going here. It's yeah, here we go. Is that showing the slides?
It is.
Okay.
Perfect.
Very good. Well, good afternoon. At least for most of the audience, I believe it's afternoon. Thank you, Ellen. Looking forward to discussing some of the very dramatic quality improvement impact that we've been obtaining with clients using industrial Internet of Things. And a colleague, as Ellen mentioned, Ron Selvig, will be helping with the presentation. Ron is a senior software engineer with Savigent Software. Savigent is the IoT platform that we used for the work that we're going to describe. There's two case studies that we're going to go through. These are actual ongoing client situations that have I think, really demonstrate the impact that IoT can have in manufacturing quality. Ron in particular is an expert in using IoT for real-time process control, and he'll help us explain the second case study and can share some of the details about how that works and the impact that was generated there. So you know, IoT can transform operations across many fronts, from R&D all the way through to sales and support, and any process really within an industrial manufacturing company. But I think in particular, quality is one of the areas where I've seen with my clients some of the biggest impacts. And if this is a chart showing some of the impacts that we've experienced working with clients, and we've sorted it here. If you think about the first order quality and compliance benefits that you can have with IoT, we've seen 10 to 25% quality and yield increase using these technologies and techniques. but also we've seen, safety and compliance incidents reduced, which really is I would call a first order quality effect. But this audience, is long time quality experts and professionals. You know that there are a lot of derivative benefits if you improve the quality. Things like workforce productivity improves as well. It enables inventory reduction, capacity throughput. If you're making it right the first time, you have less rework, your workers are more productive, your inventory can be reduced, and you get more through the factory. So I think we've seen this have really dramatic impacts with clients. So the first situation that we want to talk about, the case study, is with a very global company. It's a agricultural and food processing company. They have over 1,600 sites around the world, and many of these sites were acquired through acquisition. So there's a lot of variety in the operations and in the systems that are utilized, and also many non-standard processes. These sites and operations did not grow up in the same holistic organization. Many of them had very different origins, and as I said, came through acquisition to be part of this larger conglomerate. So there's a lot of variety, and operators and management lacked timely and accurate information. Inventory accuracy was very low, and the variation in yield and performance across the world was dramatic. There was a great need for cost and time-effective approach to upgrade these legacy plant systems and to accomplish dramatic and rapid process execution improvement. So we chose this Savigent software platform because it would enable us to make very rapid development of a management or manufacturing operations management system, a MOM for them, that would be of a size and a scope that would work for these many sites, many of which were small, and so it would be too expensive to buy a big package software application for each one of these. But we could build a tailored solution using the Savigent platform and then roll that out quickly. And the goal here was to standardize a global manufacturing operational processes, standardize them to the point where we could enforce standard operating procedures and be confident that those procedures would be executed rigorously and consistently across all these different sites. And of course, this is an old technique for quality improvement. Standard operating processes is at the core of the ISO edifice. It was built off this principle, and process control and standardized processes and rigorous execution of processes is very standard quality improvement technique. What we're going to talk about here is how we used Internet of Things to enable that kind of process definition and process control. And you can see some of that. We'll go through in more detail the benefits, but we were able to significantly improve the accuracy and visibility of information, the inventory turns and yield, and create standard executable processes across this very, and do that in a relatively short period of time over this very global network. So the idea here, what we'll look at, there was more to this solution, but what we're going to really look at here in this part of the MOM is receiving example, but the scope of the implementation was a little bit bigger than just receiving. It was really to standardize operations management, improve control and visibility, integrate information sharing across the global company. There was more to it than the example that we're going to run through here, which will demonstrate a little bit of the IoT piece of it. But we were trying to standardize those processes and automate certain parts of the process, and then finally ensure rigorous execution of those processes. And we've got a little demonstration to run through here that was critical to their plant performance management improvement, which was all about their receiving processes. Very simple process, right? I mean, we got to receive material and then put it away. In this case, it's going to be bulk liquids. But the point is that when you're doing that across many different sites around the world, it's easy for it not to be done consistently and accurately. And that was the case with this company. So here you'll see kind of two sides of the screen. On the left, you'll see what the operator would see and what he would click on, and then we'll see some screens that he would use to ensure that the receiving is done consistently and accurately. And on the right-hand side of the screen, you'll see what would be displayed inside the Savigent tool. It looks like a Visio map of a process, and it is a map of the process, but the difference between this and a Visio map is that these buttons and icons that represent actions that happen in the process actually do control the process. In other words, it's not just a picture of how you would like the process to be or how you would propose that the process should be executed, but this is actually a control map of the process. And as the process proceeds, you'll see the various buttons and icons turn red as it walks through the process. So I'll go ahead and and I'll just point out some of these. Here's this green button is where it'll start. You can see this is select the order. The operator will select the order, and then it'll go through various actions like confirming the truck, weighing the truck, taking a sample from the truck, and then concluding the receiving process. And the whole point here is that by using IoT, we were able to build this standardized process and then effectively manage execution over a very rapid period of time. So we'll let it get started here. And you'll see the arrow moves up and clicks on receiving, and then he chooses that it's bulk liquids. And when he does that, you see parts on the right turn red. And then on the left, you see he can see his schedule of all the different shipments that are due over time. And he can look on that, and then he selects the one of the orders just to look at the details under that order. And he looks at the truck that he wants to receive. And he clicks confirm, and you saw more of this turn red. Where you see a man icon or a person icon, that's where a person has an action. So here he goes in and looks at when it was scheduled to be received, and he's updating the date it was actually received, which is 2 weeks later than the schedule, but he's recording that date. And then he's checking other details about the shipment. He's adding the driver information and the license plate of the truck that's doing the delivery. And then he's making a note that this truck arrived 2 weeks later than its scheduled date. So that's the operator confirming the shipment that he's working with, the truck, and all the information. Then he clicks continue, and you see again things turn red. Now the automatic weigh station records the weight, and he's getting ready to confirm that. There was some fluctuation in the weight, so he does it twice just to make sure that he's got the correct weight recorded. And that's what he's making a note on, that he did that twice because there was some fluctuation in the tare weight. And he makes that note and he clicks again, and again we advance with the process. And now he's waiting for the sample to be taken because all inbound has to be quality checked. They have to check for content and moisture. And now he's got his sample, so he confirms that. And now he's ready to complete. He's checking over the information to make sure he's got everything. Everything's been entered. He now sees his quality details from the quality check. And where the product is supposed to be delivered to inside the plant. So now he puts his initials in, that he has done this receipt. He puts a note that it's been done properly. And then he clicks continue, confirm. And he's ready to go on to his next task. So that's a little demonstration of, you see a glimpse of the software tool that was used, at least the work flow management part of that tool set that linked to many different systems. It linked to SAP, it linked to the scale, it linked to the quality, plus the operator could make entries, as you saw. So there is one of the powers of the solution was that you could link to not only the shop floor all the way to the SAP, and you could get the information about the shipment and the truck, but also you could share information to SAP about the weight and the receipt of the order, and also you could interact with plant floor equipment, like in this case a scale. And the impact was dramatic. Increased inventory accuracy, 50% from 50% to near 100% by connecting all these systems and getting this in place and enforcing that rigor on how the process was to be executed, all receipts all around the world at all these different small operations. And as mentioned earlier, which is not uncommon with quality improvement, that when you improve the quality of the process and the accuracy, you improved operator productivity dramatically by 23% as well. So, and one of the things that was very exciting about this project was the ability to quickly build this solution, this MOM, this very focused manufacturing operations management solution for these smaller locations over a 12-week period and pilot that, then roll it out to the first 10 sites and in 12 weeks. And then, as you can see on the right-hand side here, over a period of a couple of years, roll it out to hundreds of sites. And some of the things that were included in the solution were this automated receiving, this scheduling of production, the managing of the inventory, the recording of shipments, these automated updates to SAP, and the impact was dramatic. One of the things to note in a solution like this is making that initial design robust enough to work for many sites around the world, but also having flexibility, because things are different in these very many different sites. The equipment is different, the systems that you're tying into are different. And so there has to be a core that is common, and enough flexibility to adapt to those local conditions. And that's where you really need a governance process that's overseeing the deployment of this, so that you are careful to protect the core solution, but allow the local adaptation so that it can work for these many different sites. And Savigent platform was really effective in being able to do that. One of the things I mentioned was this interconnectability between the various systems and the equipment, and that was one thing this platform really had capability in terms of proprietary technology that enables capturing and acting on lots of data. And you'll see this even more impactfully in Ron's example that we're going to talk about next, where we were doing real-time process management in terms of quality control. But the ability to interconnect with hundreds of sites, millions of reams of bytes of data and terabytes of data, and do that in a way that's very robust and fast, was very powerful. But this ability to connect both to the shop floor, to sensors and or individual pieces of equipment like a scale, but also connect to business systems like SAP and other systems that were in use around the world, that was extremely critical to making this solution successful. And then the second element was the piece that we really demonstrated with that demonstration example, which is the work orchestration, the ability to build an event-driven workflow that incorporates information from various systems, but also can and is active and acting on that information, and can incorporate operator actions, can alert the operator to things that he needs to do, can record whether he did them and what the action was, and then and impacts the actual execution of the work process. So it's a rules-based orchestration of these complex work processes. And the other thing about that map I showed you, and which you see on the right on this picture, is that is a drag and drop type of construction. So the engineers and the operating managers can build these workflows and themselves. It's not a C++ coding exercise, but in fact, it's something that the engineers can use to build the processes, refine the processes, and again, they're not just an representation of how you want the process to work. They're actually the control process for the workflow. The other thing it gives you is documentation of the manufacturing processes and the critical knowledge. If you think about ISO, where you're trying to get your ISO accreditation or renew your ISO certification, the main thing is to prove that you're executing the documented processes the way on the floor or through the business, the way they're documented in the ISO manual. And here is a tool that actually you can use to demonstrate and say, yeah, this is exactly how we do it, because this is the process. It's not just a representation of the process, but when you kick off the process and it starts to flow, you're actually, it's actually active. It is controlling the process. So it's, you don't have to interview the operator to discover that that is what he does. You have an actual record of all the runs that you made and exactly how they were executed. So there's great power here in increasing performance by driving consistency of process execution, and that was what we really were leveraging in this example. And you can get productivity and yield, which we saw, but you also can get effectiveness in the engineers and the lean initiatives. If you think about trying to do process improvement and your engineers trying to improve their processes, this is a tool that can make them dramatically more effective. And finally, you can increase and improve safety and compliance with these tools. So That's the first case example. The second case example we're going to go into here is a global data storage and data management manufacturer. It's really a company that, and the plants that we were working with that Ron is going to describe for us, it is a huge wafer fab. So this very sophisticated silicon growing and silicon manipulating equipment in these large plants to ultimately make integrated circuit chips. And in this case, we had two sister semiconductor fab plants, Europe and the US. Rapid changes in the industry we're adding complexity to the products in the manufacturing process. The number of, mostly in processes, we tried to make them simpler and simpler, but in the information technology space with silicon chips, it's gotten to be more and more integrated circuits on a chip, thinner and thinner layers, et cetera. So the number of fab steps moved from 250 to over 2,000. And lead times were extending out from 30 days to 90 days over a period of time as the product continued to improve. And this was driving large increases in labor and equipment. And there was a need for making large leaps in capability for productivity, yield, in order to counteract this, stay competitive, and stay in the market. And so the client pursued digital transformation on a wide scale, but in particular, wanted to use the technology, this IoT technology, to automatically monitor their production processes and react to those, and also automate decision making for the engineers in troubleshooting problems. And the impacts you can see on the bottom were tremendous, tens of millions of dollars in cost savings, over a 30% increase in labor productivity, higher yields and reduced defects through fault detection and advanced analytics. And so it's really extremely successful. And I'm going to turn it over to Ron, and he's going to explain in more detail how they use the Savigent technology to do this monitoring of the process for quality benefit. Here you go, Ron.
Hello, everybody. Yeah, thank you, Ernest, for covering what you did. That automated workflow was basically the product that he talked about just recently here. And I'm going to talk about our Streamline product, which, like he mentioned, a major semiconductor company has been using this product of ours for many, many years now. And with, as Ernest said, some really great results. Preventing millions of dollars worth of scrapped semiconductor wafers, which are getting more and more expensive because more and more circuits can be put on a wafer nowadays than in the past, by far. So it's critical to monitor data from these different many tools. This particular factory, the twin factories, have upwards in the neighborhood of 300 tools. Some are extremely expensive, some moderately expensive, but the fact is the engineers for these tools have to identify what is key, what is the key process sensor data that's important to them to be monitoring 24/7 or during wafer runs in their tool chambers. And this product of ours, the Streamline, is a powerful drag and drop development system, a little bit similar to the workflow, but it goes a little bit different. Basically, we can collect with our engine development, we can connect into their systems, collecting data according to their model. So we have a model designer that can design the interface. What does the data interface look like? And we can connect with these drag and drop scriptable modules, and we can actually put onto our system bus. We have our platform system bus where we can put in real time context data, sensor data, and events. context data is a named time frame with a start date time and an end date time. It's a named time frame. Like, okay, what's the name? What is the system name of this wafer that's now being processed in tool A, chamber B? And that has a starting point. So when the robot takes the wafer, puts it into the chamber, we get that event from the tool into our system, and we log that as a trigger point. So that trigger can be the trigger for a rule. It's a configurable rule that the customer has access to, a rule table. So we can do single or multiple sensors for each streamline, and it monitors data coming in at the fastest rate right now every second. Some do every 2 seconds. But we monitor that data according to the set of their rules, like the little chart on the right-hand side there. They establish what the upper control limit is and the lower control limit. And the blue data points indicate, like an example of the flow of that data that's conducive for what's important to them for a particular process. So we can customize and make several dozens and dozens of these streamlines that are running real time in parallel for each particular tool that we connect with, and we can be monitoring against their rules. So we can also do context data, sensor data, and events. An event is a single data package defined by a model, like an alarm or a product movement event. Okay, so so we basically listen for those on the bus. Okay, the next slide. A user can establish and configure sensor data input. Now here is an actual streamline in the designer stage of our product, and we've got a configuration agent there in brown, and it's got 2 different contexts, and one's like a recipe and one's the recipe step. So, and below it, we have an input, sensor data input to each of these blue processors. And then there's an alarm output in red if that data in real time during the context period indicated by those green inputs at the top go out of control. And that alarm can be in whatever format the customer wants. And what's important to him to identify what product was in that chamber during the time that one or more of their critical sensors went out of control as defined by their rules. Okay, and then this other blue one here is a general custom FTC alarm, we call it. That goes out on our bus, and then another engine that you can develop actually takes that and automatically sends emails out to technicians or engineers that are pertinent to that particular tool or process, telling them about the alarm that happened. So in real time, we can trap for what they call out of control against limit, like in here, that these are 11 standard limit processors. We also have custom scriptable processors that can go beyond just a simple, well, as you see point by point come in real time, which one goes out of control, or above or below those limits. You can also say, okay, let's average X number of points at a time, comparing the average with the limits of upper and lower, or standard deviation in real time. And it can be fairly complex even if they want to, or you can keep it simple, depending on the customer's need. And so these are all recorded, by the way, to our Historian Microsoft SQL database system. So they can go back a whole year in time for any particular tool in the factory and see what the actual data pattern was during all those product runs, you know, day by day, month by month. Okay, now the context conditions can be applied to a streamlined entity for the purpose of having containment rules, as we talked about, during specific timeframes. Model-based alarms can then be output to the bus, or our system platform bus, for processing by other engines or workflows. So we can interconnect with our own rapid development products as well as the outside world going to the customer systems as well. These streamline generated alarms can then notify the customer systems to act upon and thus complete the desired containment response cycle. Also, all output entity data sent to the bus, as I mentioned, goes to the historian database. Conditions can be also based on other sensor data or even other events being monitored. If no configured rule-based contexts are used, then the rule is called 24/7. So if your Streamline is running in our runtime system, then 24 hours a day, it's monitoring whatever you designed in the inputs to be monitored against your control limits. Now, the source of incoming bus data can be from engines, as we call them in our product, or workflows, which connect with the client network systems, and they supply the relevant equipment data. So we can move to the next slide. Okay, this is just an example of a deployed Streamline entity. It uses an editable table called the rule table to apply specific conditions for the alarm containment. An example is this one here, a light intensity Streamline with a rule called Step 2 Stage BMP. These are meaningful names to the customer for the particular process. The deployment is the main purpose for the Streamline, giving the customer an editable rule table to apply specifics for alarm containment for their data. And here encircled in red, we have a deployed Streamline with its single rule underneath it. And then on the right-hand side, you see the table. So we have a context called stage, that's a wafer stage, and then we have a wafer recipe step, which they can change, by the way. So during stage BMPVE, recipe step 2, we are monitoring the download light indicated sensor. It's enabled. The low limit is 0 and the upper is 40. And the alarm action is called notify here, which means the pertinent people will get an automatic email. And we also record in their proprietary database system, we record this alarm as well as a Streamline based alarm detected. And then there's the machine, the mock or machine, which is this particular one there. Okay, now yes. Okay, we can go to this one. And this was just to show you a little bit more what we can do. Okay, here's real time in the blue arrow. We can apply the configurable limits to the incoming data on our platform bus, either 24/7 with no context conditions or user supplied context conditions. This allows the rule details like upper limit, lower limit, window size, settling time, activation period. You might say, oh, I want to skip, okay, at my particular context period, I want to skip the first X number of values. We can do that with the settle time, for instance. Okay, custom parameters can be added as rule columns for additional elements to analyze. So that's the growth pattern of this is very highly configurable. So you can go beyond the simple upper and lower limit containment if you want to make it even more precise to depending on the data that you're monitoring. So that's basically this one. We'll go to this one now, and this just shows you. Okay, here the customer wanted to use window size averaging. So every 4 points are averaged, and then that average is compared against the limits. So every 4 as they come in, second by second, this particular data, they're averaged one window at a time. And once we detect an alarm, that rule then terminates because there's no need to go further. We've got an alarm condition that has to be carried to the customer's system for them to act upon that alarm. And one big example of this to prevent scrap is we talked to their factory system software with one of our workflows that receives this type of a Streamline alarm. Okay, something's out of control, and the engineer said if that happens, we want to prevent the operators from loading any more product onto that tool or chamber until the technician looks at it and gives the all clear. So, and that will protect because if something was processed and a pressure or temperature went out of control before that and nobody cared, that could definitely ruin these highly complex, semiconductor wafers. So there's an example that how it can save the customer's product by alarming in real time, all very configurable to the desires of the engineer who knows that tool the most, that process. So that basically covers it. Another slide. Okay, and here's some custom configuration use cases. We can do oscillation detection with upper and lower peak rise and fall thresholds, and apply a frequency limit over time. So if you see too many peaks going over this threshold, per minute, which is configurable, that will dictate an alarm. Or a spike detector, either upper spike or lower spike detection. You can do custom sensor data creation based on logic applied to incoming sensors. And you can form another sensor to load to our historian database based on one or more real-time sensors coming in. We can do context generation for custom use. So if there's no event from the tool that constitutes a context period that you like, we can base the context on other incoming data to define when a context is going to begin and when it's going to end, within we do the rule-based comparisons. And then we have a statistics generator we can do and output that against from the data coming in real time. Alarm frequency monitor, we can bring in alarm events from the tools and say, oh, in 24, give me a report on these first top 5 type of alarms. How frequent have they been happening day by day? And that's recorded as well, we can do. And then the configurable table uploader. An engine can actually request from a Streamline what its current rule table is. So if 5 different engineers have been changing values in there, we can get a report from time to time. What is the current content of that rule? So at any point in time, and these are all running in our runtime system, continuously. And we can do this for as many servers as the customer wants to purchase, and it's highly expandable, like I said. So right now we're collecting data from probably 90% of the tools at this large facility. And this one here is an example of our charting tool, and you can see at the top there, the upper part. This is a contextual Streamline, meaning there's a context period. Like here's a tool vented, a named context. It has a starting point and an end point. And you can see below in blue, there's a chamber Pirani pressure sensor with all of its data points, and that's the pattern that it flowed with during that context period. And you can just hover over with your mouse and look at any data point, and it'll tell you the exact time and value of that point. And then in the context period, if you click on that, it tells you the start date and time and end date and time of that context. So it's highly scalable as well. So that's our charting tool, and you can save all these charts in a named fashion, and you can organize it however many engineers or techs are in that, over that tool, so they can check in and check out to our system any of the charts that they create from the data that we receive into the historian database system. So that basically covers kind of a little snapshot of that. And here's a custom Streamline output. Just to show you a little bit, we can get a little more complex here. On the left-hand panel, that's a model that we've designed for a particular event. That this particular event is from our Streamline, I believe. Yep, and it's basically saying that we're calculating the slope of this incoming sensor during a particular context time frame, and if that slope goes above or below the configured limits, then we alarm out and send out the alarm. And the alarm package there, you see, can contain some highly important information about the product. It has the tool name, the tool chamber it happened in, the name of the wafer, the ID, unique ID of that wafer, what slot did it come from the load port cassette, and what were the upper and lower limits, and what was the actual value that caused the violation. Yeah, and so they can act upon it however they want, and it'll be recorded also in the historian database, and that's why it shows up in our charting tool here. So this charting tool shows you we can actually chart not only sensor data, but context data and event data. So that's a good example of a complex one. So that basically covers, the Streamline for an overview here.
Yeah, hey, thanks, Ron. Really appreciate that. You can see, I mean, one of the things I think that's particularly powerful about these two examples is, the enforcement, the standardization of processes, and then the enforcement of the execution of those processes. A pretty standard, in some ways, a very simple application of Internet of Things to empower and strengthen a process that I'd say quality improvement people have been using for decades. Here, what Ron showed, which is being used at this wafer fab for very sophisticated control of very precise processes involved in etching silicon wafers, making integrated circuit chips. Very detailed real-time control and analysis of the process to maintain control, and then alert the operators and engineers to issues for real-time correction is a much more sophisticated use of Internet of Things. And so, I mean, I think that's part of the power of Internet of Things. It has such broad application in terms of how it can be used. But anyway, this chart just gives some of those overall features within this Savigent software platform that we chose for this work that enable this capability and the impact that it can have. And then the other thing to note about, one of the things about this IoT platform that we used was this smart edge to cloud technology capability that scales. That, clearly when you're doing real-time production monitoring, you're going to be at the edge. You're not doing that from the cloud. And the example that Ron's talking through, those servers are on site, and we're working at the edge, right at the tool, right where the production is happening, to monitor very detailed sensors in that production process. But also this connects to the cloud for data that you might want to store for later analysis, data that you might want to compile with other locations or compare to other locations. So, and that's the advantage of being able to work in the cloud as well. And then to be able to scale it. I don't know, Ron, if you know the total number of terabytes that are being handled per day by those sites, but the amount of data that's being processed is just enormous.
Yes, I think it's anywhere between 5 to 10 terabytes at least.
Yeah, 5 to 10 terabytes a day. Isn't that right? Something like that.
I believe so.
Yeah, it's in the terabytes per day. I mean, it's huge amounts of data. The system is very robust, very powerful. It actually was designed with some proprietary technology in terms of the bus structure and such to enable that many sensors with that amount of data to be processed successfully day in, day out, every day, right in the heart of their production process. So really key. And then the ability to roll out across many sites is really key to this technology. And we do want to leave some time for questions. There's a few other slides here that'll be in the deck that we make available after this, but I don't want to shortchange all the opportunity for questions. Ellen, do we have questions?
Yes, we do. Thank you.
Okay.
I did want to make a comment. I was thinking about this as you were explaining this. I just read one of the many articles on our challenges in manufacturing vaccines and vaccine availability and distribution. And as I heard you talk about this and the global platform that this provides, it started to make me think about a solution like this to monitor, manage, make it visual. I don't know, maybe you should go out there and talk to them about that.
Yeah, exactly. That's a great idea. I think this, there are a lot of applications where this could be powerful, and that's a really important one, I guess.
Yeah, and speaking of that, I guess, and we'll if we have time, we'll get to that. But I was going to ask, that was one application I just thought of myself. But can you think of other applications maybe outside of manufacturing? And we can get that to the end because I do want to get some of the participants' questions.
Sure.
For Ron, is it true all problems are solved through the software? I'm not sure if he heard you make that statement or where that came from.
Well, the problems can be as simple or complex as possible, but we work with the customer to make our using our product to detect as much as possible to solve their problems. And over the years, we've solved so many of their simple problems that they've been able to dig deeper thanks to our data collection and find even more problems that were more complex. And we were able to accommodate them because of our highly scalable and rapid deployment, rapid development of this containment process. And but there's probably always some problem out there that's still a little too deep that has to just take more time. But with our tool, we've been able to let them dig deeper and get the information they need so they can, give us even the precise fit of what we're monitoring to be able to find the problem. Based on the alarms, we can send them ASAP as they occur. Yeah.
Okay, thank you. The next question is, can this software interact with robots and instruments?
Yeah, absolutely. And that actually, I'd say, I think we mentioned this. This is one of its strengths, is this, ability to interconnect with a lot of different types of equipment and/or systems, whether those are plant floor and SCADA systems, or whether it's directly to sensors and to equipments like a robot or other industrial equipment.
Okay, great. Yeah. If data is needed to be retained, how is it archived after the first year or after a year?
It's really client dependent. Ron was mentioning that this software has within its suite a thing called Historian, which is a data retention database for that data. But as it piles up, the different clients have different strategies for how they want to archive that over time, how long some of that data needs to be retained. And oftentimes clients do have their own, data lake or data management strategy, and they'll want to move it to that, use it in Historian for a certain period of time, and then move it to their database, or then archive it. But it really depends on the nature of the data and their own strategies for retention.
Mhm.
That makes
Correct.
sense. That would be individual.
Yes, and we do have, I'm sorry,
go ahead.
we do have Historian frame moving capability to the cloud as well. So
Okay.
if there's greater capacity to store for longer term, we support that kind of operation too.
Okay.
Yeah.
This question comes in regards to wireless measurements. And this individual is saying, we have seen delays in wireless measurements. How do you ensure items register for the operator in real time?
Good question. I don't know if you have any exposure to that, Ron.
Not
Wireless.
not wireless. Most of our applications are through a company's intranet, their company-wide internet, .NET type framework, or PLC, various PLCs we connect with, but it's always a hard connection,
Yeah, I'd say
Ethernet connection.
my own client experience too. We're working with a client right now. It's an automotive client, heavy manufacturing. We're automating data collection on their tools and machines, and in that case, they are hardwiring to the device. Then we can communicate via the bus after that. But I haven't really done a lot of wireless sensor application personally.
Yep.
Comment by someone, and maybe you can speak to this. He says, I find it hard to believe that it's 5 to 10 terabytes of data per day.
It's massive,
Woo!
massive amount of data. You remember there's hundreds of these tools. They're collecting every second on every sensor a data point. You saw kind of the richness of that data stream. There's a lot of data there that is being processed. That's one of the strengths. I mean, that's one of the reasons we chose this solution, is because of that capability. There aren't many solutions that can handle that.
Yeah, that's pretty incredible. What's the typical ROI of this platform?
I'd say anywhere from 6 months to a year, we're seeing those kind of paybacks. The key is this ability to implement quickly. And also the other thing I think that's key to the ROI on this is, the ability to work with the existing systems, the existing infrastructure, and not rip and replace, which always has a lot of risk to it, and inevitably puts a lot of time and challenge into a project. We can complement with using this tool what's already there, take advantage of the systems and infrastructure that's there, but you're really augmenting it and making the use and access to that data more powerful. And so we can do it pretty quickly. And the tool is very configurable. These solutions can be built very quickly and then implemented very rapidly. Like I say, it helps that you're not, ripping out necessarily what you're already doing, but you're adding this as a capability enhancer.
And so kind of circling back to what I mentioned at the beginning of the questions session was this individual says, I'm from the pharma biotech vaccine background, so we definitely need a robust platform. Thanks for sharing this. So it sounds like you've got some work to do, Ernest and Ron. You can go out and...
Yeah, thank you for that question. There is a broad application for this capability. We've really been focused, and the platform was developed working with some, really in the manufacturing sector with high-tech industries that Ron described, and then also, some of these other industries like ag and food processing and automotive. But it has broader application. I mean, these are capabilities that any process-intensive organization would benefit from.
Yeah, absolutely. Okay, well, we are at time. Very interesting conversation. Thanks for all the great questions, everyone, and for your participation. And we thank you, Ernest and Ron, for your time. And we will see you next month in May for our next LED webinar. And everyone will get if you've participated, you will automatically, again, get credit sent to you via email. So thank you again. Have a great afternoon or evening, whatever time you're at.
Thank you so much.
Bye-bye.
Yep.